Okay. Oh, it's been a while since I've done this on YouTube, so I have zero clue what I'm doing. It's great. Um, do. How much latency is there? Thanks. I appreciate that. Oh, and the chat works. Great. Okay. Things that I was worried about are doing fine. Um, so the plan for today is just to work through some problems. This is what I do on Twitch, usually, and I figured I'd do it here today because I asked, and a handful of people said they would rather have me here. So I'm just gonna be working through some problems, and why I just want to hide that. I want to hide that. On Twitch, you can just like hide the concurrent viewers, but okay, all right, now it's hidden. Um, so I'll be working through just a handful of the problems that I'll need to know how to do for, well, I'll need to know how to do similar, or it's undetermined if I need to know how to do these for the test or not. It's kind of a just a big, huge stress ball of anxiety and um, lack of clarity on what exactly I need to know because syllabus for this stuff is like super old, and then also the problems are different every year, which is expected. Um, they're also wildly different from each other. So they give us the old tests to practice from. I'm going to go through some of that or some of those for the next, I guess, like couple of hours. And folks in chat, if people pop up in chat, I'll talk and I'll address it or try to. Sometimes I can't answer the question that you've asked, and sometimes I'll be able to be like, oh, this is the thing. It just depends. So yeah. Um, what did I do last time? So again, I do this on Twitch usually like once a week at least, since the exam is like in a few weeks, and it gives me the opportunity to practice problems that I've gone through again. So last time I did this, it was right before I like had to go out of town for something, and I think I did a full exam. Or well, I did 8 problems, which would be almost a pass, or like almost a solid pass, because you have to do 9 problems of 12. So let's see, what did I leave off? Window, layer editor. Oh, yeah. So I think I did from that August 21 number one, all of that stuff, and then whatever is on the next layer. Um, so I should probably just start doing problems because I only have a couple hours to do this today. So, um, what was the last one I did? Was August 2021, number 8. So that means, oh, okay, and then number 9. So this is what number 9 was. I'm not gonna do number 9 because it's a very long problem, or I haven't figured out a short way to do it. So what it is this is August 2021, number 9. Um, so absurdly long, at least as far as I can tell. So it says that the proposition is show that every continuous image of a Hausdorff space, or yeah, of a metric space, in a Hausdorff space is metrizable if and only if X is compact. Ooh. And so the problem with this one, which I haven't looked at in a while because it is, my note on this paper is that this problem is absurdly long, which is why I wrote it in parentheses. But do I have it on me? I think I have it on me. Because one direction is easy, the other direction is um, do I not have it? Boy. Done before August. August. Where's me August? Well, 2020. I think I might have misplaced that one, which is unfortunate. But there's this thing with like there's this thing with there's an outline in this book of how to do it, and it goes over like 4 or 5 different exercises, which seems absurd because the most of these problems. So if you're doing this, it's like you have they give you 12 problems. You have to do 9 of them in I think it's 8 hours still. They might switch that on us. It might be shortened to 6. And so on average, you're like looking at problems should take you around half an hour to an hour and a half at the most. And on any given test, you should only expect like maybe 1 or 2 to be like really, really long problems. Um, so usually there's 1 or 2 that are just very quick and very easy to well, or rather, some of the problems that are quote unquote long have like shorter arguments that are not as intense. I don't know. Ooh, ooh, I think I found it. Yeah, so the backwards direction is the easy one. And it's still long. It's still worth doing. It's just the forward direction is terrible. So I guess I can do that. It's worth doing because it is like a standard argument for this stuff. But so how far am I zoomed in? I'm gonna be at 250-ish. Ooh. One thing I don't like about YouTube is that I don't know exactly how to get things so I can see stuff sometimes. Let's see if I can figure it out really quick before I start doing stuff so I can see if people say something. Uh, Hey, there we go. Okay. All right, cool. I can see things now. Do. Put you. Oh, there. If this will do the thing. There we go. Okay. So, um, so again, right, the forward direction of this is hard because it's every continuous image of a metric space in a Hausdorff space is metrizable, if and only if it's compact. So you have to show that if every continuous image of a metric space in a Hausdorff space is metrizable, then it's compact. Then the space was compact. Space X in a Hausdorff space is metrizable. It's compact. Yeah. So the backwards direction is actually easier to do. So proof And this will be backwards. So the first thing to do is that, well, just take some continuous function. Right? So let f from x to y be a continuous function, and it's onto, right? Because we're thinking about images of the metric space, so be a continuous onto map from metric space x to its image f of x, which is equal to y. Hey, well, I mean, I don't know enough about you to confirm that, or confirm or deny that statement. But yeah, this is like a common. This is a common a qualifying exam problem, whether or not it's a PhD level or a master's level. Also, for context, this is what was it? This topology exam is purely point set topology and some like logic slash set theory stuff. So I won't be doing any algebraic topology for this. Um, but let's see. So then, since x is compact, and y is equal to f of x is a continuous image, of a compact set. It's compact so oh, hold up. And then from a metric space onto its image in a Hausdorff space. Uh, oh, Nathan, come on. I don't need onto. Let f of x from x to y be a continuous map from a metric space x to its image f of x, which is a subset of y, a Hausdorff space. That all makes sense. That's what the problem says. Where y is Hausdorff. Then since x is compact and f of x is a continuous image of a compact set, it is compact. So how does this work? It's a compact subset of a Hausdorff space. Well, it's closed. It's still Hausdorff. Hausdorff is a, yeah. F of x is T2 or Hausdorff and compact. So it is normal, which is a non-trivial statement. So what does normal mean? So proof of claim, it is normal. How does this work? Oh, okay. So Hausdorff says that you can separate points by closed sets, and compact means that every open cover has a finite subcover. So if you have closed sets, every open cover of that closed set in the space will have a finite subcover as well. In this particular case. So we let A and B subset of f of x be closed sets since f of x is Hausdorff. I feel like I'm missing something, which is never good. It's also been a week since I've looked at these. Ooh. Yeah, the Hausdorff property is hereditary, so I'm not. Yeah, so we're good. If a Hausdorff space is, or if you have a Hausdorff topological space, then yeah. So if you have a Hausdorff space, then subsets of that. Yeah. Yeah. Okay. So if you have a Hausdorff space and you have a subset of the space, then it's hereditary Hausdorff, or it's the subspaces are also Hausdorff because Hausdorff is a hereditary property. It's T4 that does not have hereditary. It's not a hereditary property. It's a gross word to say sometimes. Um, since f of x is Hausdorff, for every a within A and B within B, there exists a UAB and VAB such that I have no context for that. Honestly, I'm very confused now, but that's okay. Um, so so there exists a UAB and a VAB such that A is within UAB, B is within VAB, and UAB intersect VAB is empty. So the collection of UAB, so for a fixed, I want to fix B. I want to cover A first. So for a fixed B within B, the collection of UABs such that A is within A is an open cover. Oh yeah, these are open. So they're within the topology of the space. So for a fixed B within B, UAB, A within A is an open cover of a closed subset. Oh, I don't need that. Yeah, a closed subset of a compact Hausdorff space. Compact. Well, just a compact space, which is compact. Yeah, that's what I'm doing right now. It's part of this bigger problem. Should every continuous image of a metric space X in a Hausdorff space is metrizable if and only if X is compact. So I have that the image of X is compact in Hausdorff, so I need to show that it's normal. I'm doing this because this is, even though it's a standard result, it's like it's not trivial to show it, and it also is a problem. It's usually it comes up as a qual problem in its own right at times. So so it's an open cover of a closed subset of a compact space, which is compact. So there exists a finite set S subset of A such that the size of S is less than infinite. And ooh, the cover UAB A with an S is a finite subcover. So ooh. And let's see, what is it? It's and for every A with an S, B is not within UAB. Or rather, even stronger, UAB is disjoint from just like VAB is empty. So basically I need to do the same thing on the other side. How does this work? Because you have, this is where the picture helps. So I've got my S, it can do some weird stuff. And it can intersect the other thing. I should use different colors for this, but that's okay. And there's this B that lives in the set B, right? So then this is an open cover of A, and then I just need to, there's an associated VAB as well. So, okay. Well, I can intersect them all, and those will be just, ooh, but I don't want to do that yet. So, subcover, note that each for every A with an S, this is true. And A is within oh, and B is within this open set, right? So for every A within this thing, and B is within VAB. So define B prime equal to the intersection over A with an S of VAB. And the fixed to B within B, because that's what I want to focus on. This will be the union of all A with an S of U, AB, which feels wrong. It feels like I should intersect these and union these together. So it's, what am I doing again? This is your fixed B. You have all of these open sets. It may not hit that thing. But then you have, oh, okay. So you have all of these things on the other side that don't hit those particular open sets. If you intersect them down, because there's only finitely many of them, you get an open set, which is why VB prime is important. And VB prime is disjoint then from all of the, is disjoint then from UB prime. So then VB prime intersect UB prime is equal to the empty set. And since B was arbitrary fixed, oh, before I say that, these are within the topology because of finite, this is a finite intersection of open sets, this is a finite union of open sets, so we're fine there too. So UB prime intersect UB prime is equal to the empty set. And A is a subset of UB prime. Ooh. Let that, I guess that's a V. I mean, it's an epsilon, but I just want it to be a fancy V. Equal to the set of VB prime such that B is within B, or B. So this is since B within B was fixed arbitrary, or arbitrary fixed. Because that was arbitrary fixed, we have an open, we have this fancy V thing that's all the VB primes where you just change the B that you do and you do the construction from before. And then fancy V is an open cover of so then V is an open cover of B, and as B is a closed subset of a compact set, closed subset of a compact set, it is compact. So there exists. Yes, I am preparing for PhD quals. I've already passed my analysis qual, so this is just round 2. And then I'll never have to take a test again in my life, assuming that I pass. It doesn't feel like I'm going to pass right now. Most of what, oh, hold up. Most of qual studying is feeling like you're not going to be able to do anything good enough. So like it's like peak imposter syndrome time for sure. T is a subset of B, such that T is finite. Come on, we can write infinity. Okay. So that T is finite and on CV prime, which is equal to the set of VB primes with B within T, is a finite subcover of on CV. Note that for every VB prime within B prime, VB prime is disjoint from A, and the union over the VB primes is going to be equal to there's going to be a superset of B is an open set. Well, so this is an open set, so that's half the battle, and then you just do the intersection thing again. So, okay. Subcover, da, 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 da. And for every VB prime within V fancy V prime, there is a UB prime, an open set such that UB prime is a superset of A and UB prime intersect VB prime is equal to the empty set. So we define V. Okay, did I already do anything with V? Yeah, no, I did not. So define V to be so we define V to be equal to why am I so this is the we're at the end. This is the easy part. So V is just equal to the union of the B's within T of the VB primes, and U is going to be equal to the intersection of B within T of the UB primes, which is equal to the intersection of B within T of the union of A within S of the UABs, right? Yes. Haha. UAB, right? So this is so each one of these is open, and this is a finite intersection. And so this is within the topology, and this is also within the topology. So both of those sets are open. And note that, so, and by construction, V intersect U is equal to the empty set, and A is a subset of U, B is a subset of V. Thus, f of x is normal. Okay, so that was, ooh, and I am writing too big. That's the end of that part of the argument. Draw a line. All the way down. 250, 250. Do I know of any good video lectures on general topology? Not particularly. This is something I struggled with when I was an undergrad because I didn't know where to look for topology stuff. But I would say that Munkery's topology textbook, which is this book, is like a standard undergraduate course in topology, and it does a lot of like intro to set theory things as well, or just like set arguments and whatnot and functions and stuff so that you have a good foundation for how to think about topology, at least at like the very introductory level. And then anything else I'm missing? Yeah, so I'm actually about to start my third year of my PhD. So I guess I kind of figured out later that my PhD is a little bit weird with how it does assessments and whatnot. So we have two qualifying exams instead of just having a preliminary examination um, and like an orals argument. So instead of having a prelim and an orals based on, and where orals are based on your research, we have two PhD qualifying exams, and then our like oral argument is part of the thesis defense, which also like most places have a thesis of defense in addition to the oral argument, because that's kind of the whole point of a PhD, is to define a unique contribution to your field and substantiate it rigorously. So yeah, I've been doing tests for a while now. Hopefully this will be my last one as long as I pass it. Okay, so we showed it's normal. And then yeah, this is the weird base thing. So um, the idea with the rest of this problem is to like um, so the idea with the rest of this problem is to define a basis of sets for the topology on the image. So since y is normal, so since f of x is normal, it is regular, so we let oh, can I say this? Do I have a countable base? I think I do. It's just, oh no. US metric space image. A continuous of a metric space and a Hausdorff space is metrizable if and only if X is compact. So X is compact and it's metrizable. Oh, okay. Yeah, we're fine. This is okay. So um I don't really need regular either. Why do I want regular? Because it's normal, so it's regular. It's compact, so it's Lindelof. So regular and Lindelof gets you second countable. Regular and Lindelof. another non-trivial thing. Hmm. Metric space is Lindelof if and only it's separable if and only it's second countable. Every regular Lindelof space is normal. That's not what we want. Yeah, what I said is just false, which is compact Hausdorff spaces and hence normal spaces need not be second countable. Prototypical example is ordinal spaces. Love ordinal spaces. They make me just very confused all the time. It's wonderful. Why can I say that I have a countable base? Hey. Oh, that's on Twitch. Which is fine. Um, but oh, it's funny because that like notification, the little dude I drew, the little blue guy that pops up when you subscribe or follow or do anything, I drew him like a long time ago. Well, not a long time ago, but back when I was still doing an office job, and so he just jives when I get one of those. Um, so sometimes I'll have Streamlabs open and not be streaming to do something, and like the notification will pop up, and I'll have to like turn it off. But no, it's he just jives. Blue just jives. Uh, why do I have a countable base? Symmetric space. I feel like that's what the thing is. Oh, this is sad. I should be able to do this by now. um, it's one of those things where it's like I'm disappointed because I should be able to do these arguments relatively quickly now, or understand why I get what I get out of the givens pretty quickly. But uh, it's also good that I'm having this hiccup now and not while I'm in front of a paper for 6 to 8 hours, trying to figure out what's going on. Where is Eurozone's metrization theorem? 23.12. Regular and second countable, separable and metrizable, embedded in a subspace of the Hilbert cube, or a T1 space. Those are all the same. I have normal and metrizable, which is not what we want. Regular is metrizable. What is happening? Why is this hard? Okay. I believe it's true. I don't know why, which I guess means I don't believe it's true. Uh, this is kind of how it goes. It's an image of a metric space X and a Hausdorff space if and only if it's compact. It's compact metrizable. Is that what it is? Compact metrizable means you have because it's okay. It's compact and metrizable, so it has a Lebesgue number. Well, there exists a Lebesgue number for every open cover, and the space is of finite diameter. Which I think gets you there. Well, but that's not what that means. Every totally bounded metric space is separable. Ooh. Yeah. Will X be a metric space? If X is compact, then it is separable. Sad day. Yeah, it's because it has finite diameter. Part of the reason why. That's annoying. That's so annoying. Okay. Um, all the way up to the top. Just to write this down because I needed to look it up. Right. So okay. Since f of x is a compact metric space, it is separable. So in particular, right? So it is separable in particular. F of x. Oh, that's not true. I'm going backwards. X is compact. Continuous image of a compact set is compact. So it's compact and normal. I need to show it's metrizable, which is you do by okay. That's the disconnect. Um, hey, topology is my field of interest, so I don't, I mean, I agree, but I also, I'm I don't feel that way about it all the time. It's part of my field of interest. My field of interest is topological dynamics or topological dynamical systems. So I work with topology a lot, or try to think about it a lot. Um, so since f of x is a compact, oh, that's not what we want. So since X is a compact metric space, it is separable. In particular, X has a finite diameter. Um, of X is less than infinity. So um, so X is totally bounded. Right? Yeah. Okay. I'm just gonna write down its finite diameter because I don't want to think about this more. Um, oh, I wish I knew more algebra or like or more was more comfortable with it. I did study for the qualifying exam last summer and I felt really good about it, but then I just got totally wrecked by that test. It's like it's considered the harder or one of the hardest PhD qualifying exams where I'm at for my PhD program. So um, makes sense. Yeah, no, I'm not doing. Excuse me. I'm not doing any algebraic topology. This is all just point set topology and set theory slash ordinal space stuff. Um, so there's no one at my institution that does strictly algebraic topology. There's some, I think there's one professor where she does some like homological algebra, which I guess is like close to, or I guess is algebraic topology in some sense. It has that as an interest, but it's not like the strict research field of any given professor where I'm at. So they don't ask us about it on qualifying exams. Mostly because the people that make up the committee for this particular exam is a topologist, a topological dynamicist who's on sabbatical, a set theorist slash, I guess, logician. Well, he says he's a logician, but a lot of his stuff is set theory, so it's confusing. Um, and then the third guy who's on the committee is a model theorist, which is super intense. At least from because I know nothing about it, or not much about it. It's the whole like, how do we do math? Or what makes math math? Meta math. Actually, it is separable. So let's B be a countable base for X, and let C equal to the collection of finite unions of elements from that base. Then we define we define D to be equal to y minus fx minus c, such that c is within fancy C. So there's just this random collection of sets, and we take the whole space and we remove. Well, I guess I just want to look at f of x here, and I want to say that this is a base for f of x. In some sense, that's true. I think at the best, or at the, I think a lot of people, quote unquote, do math without actually knowing that they're doing math. Because at the end of the day, a lot of math, at least the way I think about it now as a grad student or as a PhD grad student, is that it's a lot more just being able to construct a logical reasoning um, and communicate it in a coherent way. Well, I say coherent, but then you look at what mathematicians write, and eh, then you kind of need to know math to do math. So we have this collection of sets D, and the claim is that f of x minus f of x minus c for some c in fancy C is open for every C within fancy C. So the proof of claim is that, well, how does this work? Since X is compact, and since X is compact and C is a union of open sets, X minus C is a closed subset of a compact space which is compact hence f of x minus c is compact since it is a continuous image of a compact set. So as f of x minus c is compact in a Hausdorff space, it is closed, and thus f of x minus f of x minus c is equal to f of x minus c complement, where the complement is in f of x is the complement of a closed set which is open. The claim, and then the last part of this is to show that D is a base for f of x. So claim D is a base for f of x. Oh, where did that go? How does this work? So a base just means that for every open set you can express it as a whatchamacallit, as a union of basic open sets. So I don't think that's what I'm going to do though. Okay, well, I'm just gonna go through the argument I already have down and see how that goes. So, let's do that. So, let y be in an open set, which is within the topology of f of x. Then f inverse of y is a subset. Well, yeah, so it's a subset of f inverse of u. And since f of x is Hausdorff, y is closed, and thus f inverse of the singleton y, which is I guess it's the same as if I just do f inverse of y, because it's not a one-to-one function. So this is just a set. This f inverse of y is compact. It'll be a closed set in its pre-image, so it will be a closed subset of a compact set, which is compact. So since f inverse of u is open, there exists a subcollection of the basis on x such that f inverse of y is equal to the union of this subcollection. Or rather, it's a superset. Yeah, f inverse of y is a subset of that union of that collection. And so right? So this is the case, and this is a superset of F inverse of Y, and this guy is compact, so there exists an S subset of I. S is finite such that F inverse Y is a subset of the union of B, I within S. Then taking C to be equal to the union of that finite collection of BI, or that finite subcover of that collection of BIs, which we can, this C is within the fancy C, right? So this C is within this fancy C thing because it's just all the finite unions of things within the base. So I'll be able to form a set from T out of it. So taking C is equal to that union. F inverse of Y is a subset of C, which implies that F inverse of Y is intersected with X minus C is empty, which means that Y is not within F of X minus C, which means that Y is within F of X minus F of X minus C. Thus, density is a countable base. For Y. And as F of X is normal, it is regular. So F of X is both second countable and regular. Hence, by Girson's metrization theorem, F of X is metrizable. I think that's it. Every continuous image of a metric space in Hausdorff space is metrizable if and only if X is compact. So I went the backwards direction. Forward direction, I have no idea how to do, quite honestly. I know that there's an outline that I have not spent enough time trying to think about. But the backwards direction I'm going to leave as I don't know right now. So backwards direction is, let me do this. Willard, general topology. And this is what exercises. Oh, there's certain exercises to which this applies. Normal. All the way. Not that one. Not it either. Where are we at? Wallman basis problem. Metrization problems. Yeah, so it's Is it 23J? Yeah, 23J through 23L number 2 is, so it's what, one, two, wait, it's 1, 2, 3, 4, 5, 6, 7 problems. 7 total problems. Um, but I haven't been able to find a resource for it outside of this book and that outline. So I'm very confused. Because usually there's usually a quick argument for some of these like two-part problems, especially when the first direction is a bit longer. I kind of did overkill because I probably could have just said that um probably could have just said that I could have just skipped this normal argument, but it's a good thing to practice. It does come up. Um, oh, let's see. So I'm gonna put down the LOL because it's not done, but there's an argument somewhere out there for it. Oh, and that's supposed to be the forward direction, not the backward direction. And I'm doing terrible on time, I think, at least, because usually I'm pretty good about. Let's see, where are we at? Where are we at? Oh, oh that's interesting. Okay. Um, where are we at? I just want to see where YouTube makes things weird sometimes. That's okay. Okay, I can't. Can I see it here? Yeah, okay. All right. So I think I have time for at least one more. And this is three different problems. So I'll probably do this one and then it's three problems in one, but I'll probably do this one and then I'll have to go do more. Um, yeah, I'll have to go after another one. So I'll do that. Do the counter examples problem. Or at least it's not a it is a counter examples problem, yeah. Down. And then what are you doing? Doing okay? What is up with this? Weird. Weird. Okay, okay. Uh the internet just doing all the things. Okay, so this is August 2021, number 11. Or no, number 10. Number 10. I want it to be a different color too. Image. Layer editor, we can lock you and then just, that's too yellow. Okay. This one is, give an example. Of the following. With proof. So A is a separable first countable. Oh. Separable first countable. Space, which is not second countable. And then we've got, what else? B is a quotient of a second countable space. Which is not second countable. And then C is a subspace of a separable space. Which is not separable. So, examples. So A, this is just the Sorgenfrey line. So this will be, let me change that as well. Where? Window. There we go. Everything's back. So examples. First one, A is Sorgenfrey line. Which is E tau E, which is just equal to R with tau lower limit topology. So, proof. First off, it is separable. Let Q, or rather consider Q a subset of E, right? Because E is just the real numbers, so the rational numbers are hanging out. So the rational numbers are a subset of the Sorgenfrey line. Then for every basic open set, x to x plus epsilon, for some epsilon greater than 0, Q intersect x plus epsilon is non-empty because of the density of Q and R. Well, I guess I shouldn't say that because That's not what it means in this context, right? Because density is a topological property, and I'm using it in the analysis sense in this case. So I guess it's the Archimedean principle, right? Is that what it's called? It's been a while since I've taken real one. Archimedean principle. Math. Archimedean property. Yeah. And let's see, Archimedean property for rational numbers. Anyway, I'm pretty sure this is at this point in my mathematical career, this fact is not something I would have to prove on a topology qual. Because it's a real analysis thing. Um, and then for first countable, so first countable note that x to x plus 1 over n for n within the naturals is a countable neighborhood base for x. So we do have a countable neighborhood base, which means for every x within the space. Let's just say for any given x within E, that is, if if U is open and tau E and x is within U, then there exists an epsilon greater than 0 such that x is within x to x plus epsilon open, which is a subset of U. And so there exists an n large enough such that x is within x to x plus 1 over n open, which is a subset of x to x plus epsilon, which is a subset of U, and we're good. So we're good there too. For not second countable, suppose E was, or the Sorgenfree line, was second countable. Then there exists B equal to BI, I within the naturals, a subset of the topology on E, which is a countable base. For the topology. let epsilon greater than 0 be given. Then for every x within E, there exists a b and x within fancy B such that b and x is a subset of x to x plus epsilon. And x is within b and x. If x does not, so if y is less than x, strictly less than x, then y then there exists an epsilon prime such that y to y plus epsilon prime is does not intersect x to x plus epsilon. So in particular, oh, but this is weird. How's it going? This is not supposed to be difficult. Oh, that's true. And so for if y is less than x, then there exists an epsilon prime such that that's true. Oh, I'm fine. This is okay. Then b sub n y does not equal b sub n x, as y is within b sub n y, yet b sub n x is a subset of x to x plus epsilon, which and y is not within x plus epsilon. So the map which goes from, which is, so it's of this form, so it's n with whatever you plug in from e to the naturals, is injective. So yeah, so it's injective, yet E is uncountable. And N is countable, which is a contradiction to Cantor-Schroeder-Bernstein. Thus, E is not second countable. And that completes A. The next, B was what? A quotient of a second countable space, which is not second countable. Um, so B, how did I do this? Okay. So B, I'm going to say, I'm going to call this the integer flower topology. So how this works, or the interval flower topology. So um, so how this works is that is let R be our second countable space. And it's second countable because it has a countable base b equal to the collection of balls of radius 1 over n about a rational q, so such that q is within the rationals and n is within the naturals, is your countable base. And define tilde an equivalence relation where for a particular equivalence class within this equivalence relation, it's going to be equal to the integers if x is within the integers, and it's going to be equal to the singleton x if x is not within the integers. So what this does is you've got your line R. So you get your line, you have the integers along that line. And then when you move over, oh, I need to turn off the line thing. Right, so you move over by tilde, right? So you've got R, you move over by tilde, and what you get out is you get, well, you have the equivalence class that is all of the, so this is where all the integers go, and then everything else is its own point, so we get all of these guys. You get countably many petals. Where this is going to be now, this is like the open interval from 0 to 1. This is the open interval from 1 to 2. It goes on, and then it'll be the open interval from whatever you want, right? So x to x plus 1. And you have one of these for every single integer. This is r mod tilde. Ooh. So what do we do? So suppose r mod tilde is second countable. Then there exists beta prime a countable base for r tilde, and we consider an open set U prime within the topology of the quotient space, an open set containing the equivalence class Z. And so for every such U, which is within the quotient topology, there exists a B prime. That's okay. I half the time don't know what I'm doing either. I can tell you the words of what I'm doing. So I am so this is a qual problem that I'm just practicing the argument for, and I happen to be doing it on the internet, uh, which is a quotient of a second countable topological space, which is not second countable. So I'm doing some weird stuff with the real line and make it into a flower. And that flower has infinitely many petals, and those infinitely many petals are going to be what causes the problem, is the less formal way of talking about what I'm doing. So I'm just being rigorous now about why having infinitely many petals is going to be an issue. Um, so so for every such U prime within the quotient space, there exists a B prime with within fancy B or countable base. Oh, come on. I can write. I swear I can. Just maybe not right now. Exists a B prime within fancy B prime that also contains Z. Or I guess I should write that the other way, such that Z is within B prime. And so now that I have like the description in terms of the quotient space, I'm going to translate that to the original topology. So then B prime corresponds to a saturated open set with respect to the equivalence relation. Such that B prime, or so B prime corresponds to a saturated open set B such that the integers are a subset of B and in particular for every n within the integers there exists an epsilon sub n between 0 and 1. So there exists a 0 less than epsilon sub n strictly less than 1 such that n minus epsilon n and n plus epsilon n is a subset of B, which is a subset of U, the corresponding, where U is the equivalence relation saturated open set corresponding to U prime. Ooh. And in particular, as found CB prime is countable, there must only be countably many B of this form. So the B's may be identified with a list of epsilon sub n's. So all the possible B's be listed according to epsilon sub n for each n within C. That is, we have a B1, which comes from epsilon 1, epsilon negative 1, epsilon 2, epsilon negative 2, and so forth. And that is the first epsilon. And then we have a B2, which is epsilon 2, or well, still it's 1, negative 1, 2, negative 2. This will be a 2 up here. We have that all the way down. So this is a Cantor diagonalization argument. And so basically what I'm doing is that I have a countable thing, so I should be able to put it in this infinite list. And to show that that doesn't actually work, I can diagonalize my way out of the list by focusing on the diagonal elements. Oh, cool. My paper was just submitted, the final version of it. Yay. Okay, that's fun. All right, cool. Um, I'll get to be happy about that in a second. I mean, I'm happy about it now, but uh, that's great. We just got the email, like, I think a few days ago, where they're like, oh, we're done reviewing your paper. Now you can send us the final version that we've agreed upon. And so we just sent that over apparently, which is good, which means I'll be able to put publication expected on my CV, which is great. Okay, anyway, so all possible B's may be listed according to the epsilon n's. For each n within C, that is B1 is this thing, B2 is that thing. In particular, we want to diagonalize out of it, so define then B star, which is going to be equal to an open set U. I don't care about, I don't need to do that, such that B star corresponds to a list of epsilons, just like everything else. Where epsilon star of f of I is strictly less than epsilon I fi, where I is a natural number and f, which goes from the naturals to the integers, is the usual bijection f of I is equal to, well, it's going to be negative I over 2 if I even, and I plus 1 over 2 if I odd. Right, so 1 will go to, hold up, is that what I want? Yeah, 1 will go to 1, and then, so 1 will go to 1, 2 goes to negative 1, and so I'll, in particular, right, so in particular, there does not exist in BI, which is a subset of B star, which is a contradiction. So R mod tilde is not second countable. And so essentially what I just did, right, is that on each one of these petals, on each one of these petals, you put some interval. Between it and the natural number that you're thinking about. And then you make, and you have a ton of different ones of those, but you have countably many of them, so you can find small enough, you can find small stuff where it just misses the interval that you wanted on each part. So you'll have no set of intervals that you, on those petals that you had specified in the countable sense in this list. In this list, will occur in the one that you constructed. And that's what diagonalizes you out of the list and makes the countable thing an uncountable one. So yeah, so that finishes that example. And then last thing I'm gonna do today before I go, because I got other stuff I gotta do, is, which, I mean, it's just more problems, but it's just the problems that I haven't done already and don't need to review. It's the problems that I need to figure out how to do for the first time. This is what's happening in offline. So it takes me about like 3 times in order to figure out how to do a problem from memory without having to think super hard about what to do. So what you're seeing, or like what I've done on most of these, is like either my second or third attempt at a problem, where I still may have to look at stuff. But after that, I usually have it. Um, so, last one, example. This is, oh, no. I feel like a red. I don't want to do Baker Miller pink because that's just the antagonist of color. I guess purple is fine, or lavender, whatever you want to call it. So example C So the more plane. Way too far in. Yeah, I'm way too far in. 250. So the more plane, let h tau m be the upper half plane h with the more plane topology. That is the one generated by the generalized neighborhood basis construction. With Cx is equal to the standard balls of radius x about epsilon intersected with the upper half plane if x is not within is not in the x-axis, so it's not within. I want it to be the closed upper half plane because I want the real axis included. So x is not within x comma 0, such that x is within R. I can write that smaller. Closed if x is not within x 0, such that x is within R. And then otherwise it's going to be it's the pointed disks. So it's going to be the ball of radius x comma epsilon intersected with the upper half plane unioned with the point x if x is within or otherwise. Okay, so if it's on the x-axis, it'll have. So these are the pointed disks. Oh, and it's not x. It's going to be. Oh, so you're on. So you're on the x-axis. It's going to be a disk above it, and it's going to be of radius epsilon. So you're going to want to go. How does this work? It's at. This is the vector x, so it's going to be the ball because we're in the plane. And this is the vector x is not within that set. Oh, thanks. I appreciate that. I haven't seen you in forever either, so I'm glad you still exist. um, but yeah, things have been going well. Aside from the like constant stress and anxiety about this test, which happens before every qual. Um, Other than that, I'm good. So this is the ball, release that. And I moved that back because I wanted to, so it's the ball with respect to the standard metric on the plane. The x coordinate is going to be x. The height of that thing will be epsilon, and the radius will be epsilon. So what this looks like is so visually, you've got this diagram. So line here is your upper half plane. And then at a point in the upper half plane, you'll have the normal disk. I guess I can do this with a circle, right? Because that is a tool, because I'm in a drawing program. All right, so you've got these things. Oh, not quite that. And then we just remove, we intersect that with the upper half plane. And they're open, right? So I have some dashes going on, right? So this is for an x that is not, um, this is for an x that is not on the real line. And then you can also have a normal circle if you are off of the, if you're far enough away and your epsilon is small enough, you can have just do a normal circle as you would expect. But then if you are on the x-axis, that's where things get different. So here, then you've got like an epsilon that you're looking at. I'll call this length is epsilon. And then from that epsilon, right, so it's so this is your x comma 0, right? X comma 0. And you go up epsilon, so this point here is x comma epsilon. And the disk is then, well, it's this one. And it includes the point on the x-axis, but it doesn't contain anything else on the border of that circle. It's just the inside. So you get these open sets. Are the three possibilities. So note that Q intersected with the upper half plane is still separable. Or is still a countable dense set. As every generalized neighborhood basis element intersects it, so every open set will intersect it. So as for every C within CX, C intersect Q is not equal the empty set for every X within H. So for every U within tau, U intersect Q is not equal to the empty set either. Or rather, Q intersect H. Or I guess I could just say, oh, and I also need to be more careful because it's not Q, it's Q cross Q. It's the rational pairs. So countable dense and C is within CX. So C intersect Q cross Q is not equal to the empty set for every X within H. Vector X is an ordered pair. Ordered pair. Ordered pair. And then for every U within tau, U intersect Q cross Q intersect H, the upper half plane is going to be also non-empty. This is the more plane topology. To show that it's not that it has a subspace that is not separable. So to show to see that so to see that the Moore plane has a subspace which is not separable, we just look at where the weird stuff happens, which is on the real line, right? So the non-separable subspace. So if we look at the real axis, so looking at, do I have room to do this? Oh yes, we're gonna finish right at the end of the page. This is gonna be great, at least for me, because it's just satisfying. Okay, so looking at the set of x comma 0 such that x is within R, then tau A as a subspace topology of of the Moore plane topology is discrete, right? Because it's going to be just the open sets are going to have because the subspace is just all of these points on the real line. The subspace is going to be, you take an open set, it's going to contain one of these pointed disks, and you're going to intersect it with the real line, and you're just going to get that particular point. So the subspace topology of tau A and the Moore plane topology is discrete, and A is uncountable. So A cannot be separable. And that completes the argument for those three examples. So the Moore plane topology, the interval flower topology, and the Sorgen-free line give the examples of A in reverse respectivity. A separable first countable space, which is not second countable. B, a quotient of a second countable space, which is not second countable. And then C, a subspace of a separable space, which is not separable. And it's 1 o'clock on the dot. This is great. Okay, cool. So yeah, that's it for today. I usually do these things on Twitch, just because I think YouTube has its own specific type of content, and that works well on it. And Twitch also like gives me freedom to do other things. So like in the past, I've used Twitch to just go through things that I'm reading at the time, or to do problems about the stuff that I'm reading, or to do this. But it also lets me do things that are not math, which I have done in the past as well. So I may do this again on YouTube at some point, but for now at least, I'm gonna keep the two. Well, yeah, I'll look at how this went because I haven't been looking at like metrics and stuff. So I'll see how this went, and I will figure out what I'm gonna do. But I'm still gonna do this, I think, majorly on Twitch, just based on how I feel and the vibes between the two platforms and what I put out on YouTube versus what I do on Twitch. But yeah, so that's just a taste of some of the math stuff that I do, and all of the right. So I think I did like what? Not even two problems. It was 1.5. We did this one, the one direction of this one, And then I did, which contained another problem that's a normal qual problem. And then I did this one, which was 3 different problems, all of which could be their own short little qual problems. But yeah, that's basically it. I'm gonna go put my head back into a book and do more of the problems that I have not yet figured out how to do or have to think a little bit more about that would not be conducive to sitting on stream and staring into the ether while my brain runs wild about this test. So that's it for today. Thanks for stopping by. This will be, I think, unlisted after I'm done. I'll figure that out. I haven't figured out if I'm gonna post it as a thing or not. But yeah, thanks for hanging out for this little experiment, and I will see you when I am able to justify to myself that I can prioritize something other than the one thing that stands in between me and doing the job that I have always wanted to do, which is pass this test. So